One of the most basic applications of derivatives that you've learned throughout calculus is the concept of velocity and acceleration. And so, since these vector valued functions represent the position of an object in space, and it is 2D space or 3D space, we could essentially talk about the idea of velocity and acceleration based off of our position function. Because remember, we're talking about the position of an object in space, so our vector valued function is our position function, right? It tells us where an object is at any given point in time. And what you know from Calc 1 is that the first derivative of the position function is the velocity function, and the second derivative of the position function, or the first derivative of the velocity function, is the acceleration. Why? Because what does velocity mean? It's the change in position over time. Derivative measures change. So if you take the derivative of the position, you should get the velocity. And what is acceleration? Acceleration is the change in velocity over time. Well, if you take the derivative of the velocity, which is the second derivative of the position, you would get the acceleration. Here, we're just describing everything in vector form with vector valued functions than we are with real valued functions. In Calc 1, you talked about the idea of velocity and acceleration in real valued function form and derivatives of each. Here, we describe an object's position using vectors. And so we're going to talk about the velocity as a vector and acceleration as a vector, which in lots of instances is actually more valuable. Thinking about velocity in vectored form and having vectors be comprised of two components, both magnitude and direction, would make a lot more sense in the concept of what velocity describes. And the same thing should go with acceleration. One thing you know about velocity is velocity really describes two things. Okay, velocity describes one, which direction you're going in, and two, how fast you are going. So when you got a velocity in Calc 1, and you found like the derivative at some location, say A, and that was your velocity at A, and you got a number of, I don't know, -3, okay? Let's say feet per second, whatever it was. You had to look at that value you got, and that value really described two things. One, the sign gave you the direction, and the number itself, or the absolute value of that velocity, gave you the actual speed, how fast you were traveling. And so there were two components to this value you got as a velocity. Well, vectors have those two components, right? Vectors have both direction and they have magnitude. Well, the direction, very simple. The direction of the velocity vector is the direction in which you were traveling. So if I look at velocity as a vector, the direction that that vector is pointing should be the direction. So this is the velocity vector, okay? The direction in which that vector is pointing would be the direction in which you were traveling. That's similar to this sign. Remember, when you got a negative as the sign of the velocity at a particular location, that just told you you're either moving up or down or left or right, forward or backwards, I should say. So the fact that this was negative would tell me either I'm moving down, so if I'm dropping a ball off a building, or if my car is going in reverse. If this is forward and my car is going in reverse, that would be the negative. And then the 3 told you how fast you were going. Well, the magnitude of this vector would then tell me how fast I'm going. So the magnitude of the velocity vector should give me the speed. Well, the velocity vector is just the first derivative of the position vector, so let's let r of t be our position vector. The magnitude of that derivative would be my velocity. It would be my speed, sorry. So again, looking at these in terms of vectors actually seems to make way more sense than to think of them as real valued functions, because of that idea of how velocity really gives you information, and it gives you information in two parts, and vectors are all made up of two major things, magnitude and direction. All right, so here we go. Here's a very simple question. Find the velocity, acceleration, and speed for a given function in vector value notation, okay? So velocity as a vector, acceleration as a vector, speed as a value, essentially. So very simply, for A, we would just have to figure out what r prime is and what r double prime is. That would give us our velocity and acceleration vectors. This should be very easy to do. We do it component by component. So for what we get, 3 cosine t, and this would be 3 sine t. That would be our first derivative. That's our velocity as a vector valued function. And it's based off of t, so this is actually a whole bunch of vectors, right? That's the thing with a vector value function. You don't just get one vector, you get a whole series of vectors. And we'll talk more about what this looks like graphically in a second. But let's just find these things. And then 2, what we're going to do is the second derivative. So let's do that again. So we get 0, we would get negative 3 sine t, and we would get 3 cosine t. And that's our acceleration vector, okay? Velocity vector, acceleration vector. Again, easy to do. Derivatives of vector value functions is simple. But again, this is a series of vectors. And so this would describe, how fast I'm going if I looked at the speed. So let's look at the speed of this, okay? Break that down a little further. So how are we going to do that? Well, it should be the square root. It's the magnitude. So the square root of 4 squared plus 3 cosine t squared. So that would be 9 cosine squared t plus 3 sine t squared. So that would be 9 sine squared t. We could simplify this a little bit here. I could pull the 9 out, so I get 16 plus 9. I have cosine squared t plus sine squared t, but we know sine squared plus cosine squared equals 1. So what do we get? We get the square root of 16 plus 9, and that gives us the square root of 25, so 5. So our speed is 5, okay? Now, this answer is not dependent on t. Remember, this is a series of vectors. This is all the velocity vectors. And when I find the magnitude of all the velocity vectors, I get this constant, 5. That's going to be a pretty important idea here of whether or not this value that we're calculating, the magnitude of r prime, ends up equaling a constant or not. In this case, it did. It's not always, though, right? We're not always going to be able to get t's to just disappear out of this thing. Because of the Pythagorean identity, we made this equal 1, and the t's just disappeared. Most times, the magnitude of r prime will equal some function of t, okay? Most of the time, okay? But sometimes not. And what happens is when it doesn't, when it equals just a constant, okay, that tells you that the velocity is 5. For any value of t, the velocity is 5, which means that this object that's traveling along this position function is traveling at a constant speed. The speed, regardless of t, is always 5. That doesn't happen with every example, okay? It happens with this example. In this case, this one is a constant, but sometimes you're going to find that the speed equals, 3t, okay? In which case it's dependent on t. So at different times t, you would get different speeds, which means you have a variable speed, which is very common, right? It's very common to have a variable speed. But, you could also have things traveling at a constant speed as well. And so that's what we're looking at as the magnitude of r prime telling us the speed. It's not always going to be a constant, is what I'm trying to show you here. Sometimes it will be a function of t. And we'll see that in the next example. But calculating the velocity vector, the acceleration vector, and the speed is very easy to do. Again, I'll show you the graphical interpretation of what we're doing here. But right now, that's the computational aspect. All right, let's look at the other example. Let's get rid of all this. All right, and do this b. Derivative in b, maybe not as easy to do as a was, but still not hard. We should be really easy when it comes to derivatives. So let's change up the color. I like green. So I'm going to rewrite this. This is log t. I'm going to write this as t to the negative 1 and t to the 4th. That's a much easier way to take the derivative here with this second component. So r prime in this case, which is our velocity vector, okay, put the little vectors on there. is going to be 1 over t, negative t to the negative 2, and 4t cubed. Okay. Second derivative, which is our acceleration vector, is going to be, well, this is now t to the negative 1, so that's negative t to the negative 2. This one will be, what, 2t to the negative 3, and this will be 12t squared. Okay? If we want to find the speed, we need the magnitude of r prime. In this case, the square roots of 1 over t squared plus this squared, so what's it going to be? T to the negative 4, because power to power, plus, 16t to the multiply 6. Okay. And you kind of see what's happening in this one. I'm not going to go too far with this. We could simplify this a little bit, I guess. This will come to the denominator. I could have a common denominator of t to the 4th. So I would get t squared plus 1 plus 16t to the 10th now. The t's aren't going away is the whole point here. This speed, this is my speed, is definitely going to always be dependent on t. So when t equals, say, 1, I can plug that in, and I can figure out what the speed is at that specific location. When t equals 2, I can plug it in here, and again, I figure out the speed at that location. But it's definitely going to be dependent on t. So this object that's traveling along this path is not traveling at a constant speed. The speed is a variable speed in this case, which is, again, very common to happen. Probably more common than a constant speed is. But that's going to be a pretty important concept. What happens with this piece right here is going to definitely affect a lot of things as we move through this chapter. And when it's not a constant, when the magnitude of r prime is not a constant, computationally, things get a little bit trickier. Okay, let's just say that. All right, let's look at this from a graphical approach. Okay, so let's look at this picture here. There's a couple of things. You see the blue curve, that's going to be your position function. Okay, so this is your r of t. Also, I'm doing all this in 2 dimensions, so it just makes it easier to draw. So r of t is your blue. Your red represents your velocity vectors, so that's v of t. And the black represents your acceleration. Okay. So we could say we have a position vector valued function. And remember, position vector valued functions essentially are tracing out curves. So this curve was traced out through a series of vectors. Okay, but nonetheless, that's the curve that describes the path that a particle is traveling on. It's also a directed path. You see the arrow tells us we're going from here in this direction. All right. Then what the red vectors represent are the velocity vectors at given positions. So if we are at this position right here, okay, at that position right here, this red vector represents the velocity vector at that location, and this black vector represents the acceleration vector at that location. And so notice a couple of things here. One is that this velocity vector is very long, and the magnitude of the velocity tells me the speed. So the speed at this location, I could gather, is fairly fast comparative to, say, the next velocity further down the road. So that is definitely something to note. Also, the direction in which that vector is pointing is the same as the direction in which I'm traveling, right? I'm traveling in this direction along the curve, and this is the direction that I'm pointing. And then I'm going to move on to the next velocity vector before I start talk about the acceleration. Look at the next velocity vector. Still in the direction I'm traveling. The next one's turning a little bit because the curve is turning. So it's pointing that way, it's pointing that way. And all of these are pointing in the direction that I'm traveling along this curve, okay, at each given location. Also look at the magnitude of each one of these velocity vectors. Here the velocity vectors are getting smaller in their magnitude. So that means as far as speed goes, my speed is getting reduced. It's not as fast here as it was here. And then it's speeding up again as I go a little bit further. All right. Well, that's exactly the change in the speed is what acceleration talks about. Now we're going to talk about this acceleration vector. Notice that all these vectors look like they're relatively the same magnitude. Well, if they're relatively the same magnitude, that tells me that the acceleration is relatively the same all the way through. It's a fairly constant acceleration. So it's changing in speed, but the acceleration versus the deceleration, whatever you want to call it, is relatively staying the same. So remember, acceleration talks about the change in the speed. Also notice that the acceleration is pointing inward on the curve. So the direction that the curve is turning, all these acceleration vectors are pointing in that direction, inward on the curve. As opposed to if my curve, say, maybe did some sort of wiggle like this, the acceleration vectors in here would point kind of inward, and then at some point they would flip and they would start pointing this way now, would be my acceleration vectors. So the acceleration vectors always do that. They always point in the direction that you're sort of turning. And kind of think about that as if you were driving in a car and you were to take a quick bank, right, in the car, you were to make a sudden, turn in the car. The acceleration of your body in the car and how to kind of pull you around that turn. That should all make sense. But just sort of describing the velocity and acceleration vectors as they relate to the position vectors graphically from what we just computed computationally, we would see this. Now, if we had a constant velocity, okay, if we had a picture with a constant velocity, each one of these red vectors would be the exact same magnitude all the time. So this one, this one, this one. We would draw them all as the exact same magnitude. And we would see, oh, we have a constant velocity the whole time. We don't have this longer velocity here and a shorter velocity here vector. We have the same velocity the entire time. But key things, the velocity always points in the direction that you're traveling. The magnitude of velocity tells you the speed, and acceleration always points to the direction in which you are turning. Okay, so all this acceleration is all going in this direction. All right. Here's another velocity acceleration question, but worded a little differently. All right, if I just say find the velocity, find the acceleration vectors, very easy to do. This question isn't even that hard either, but you have to think for a second. So, a moving particle starts at an initial position, so 0 would be the time, this is where it starts, time of 0, r of 0 at 1, 0, 0. That's its initial position, based off of that vector's location. And it also has an initial velocity, so when time is 0, so that's why the 0 is here inside this velocity vector, but the initial velocity is I minus j plus k. So did that one in IJK notation, did the other one in bracket notation. No real reason. All right. Its acceleration vector is given by 4ti plus 6tj plus k. So find its velocity and position vectors at time t. All right. Find its velocity and position vectors at time t. In this case, I gave you the acceleration, and we need to find the position and velocity. In this case, this is the reverse of what we did in the previous examples, right? In the previous examples, I gave you the position, and then we had to find the velocity and then the acceleration. Here, I'm starting acceleration and going backwards. Well, if we use derivatives to go forward, we should then have to integrate the acceleration vector to find the velocity vector. And we should integrate the velocity vector to find the position vector. And that's it. Pretty simple. A couple of little things we worry about here. These are integrals, in this case, indefinite integrals. And so we got to worry about the constant of integration here. And we integrate using indefinite integrals with vector value functions already, so you know how the constant works, but just something you got to watch out for. And so if we do the integral of the vector 4ti plus 6tj plus k what would we get? I like doing it in bracket notation, so I'm going to do that instead. I'm going to get 2t squared plus c, so I'll say plus c1. I'll get 3t squared plus c2, and t plus c3. And that's just integrating each one of these individually. And since it's an indefinite integral, they each would have a plus c, but I got to label it as different c values for each accordingly. Now here's the thing. We don't know what C1, C2, or C3 should be right now. This is not just one velocity vector, right? And that's what we're finding here. This is the velocity vector. This is not just one velocity vector, because if C1 was 3, we would get 2t squared plus 3. If C1 was 5, we would get 2t squared plus 5. So if we want to find the exact velocity vector, we need some more information about the velocity itself to be able to figure out what specific vector are we talking about here. What is C1, C2, and C3? That's where this comes in. Having the v of 0 equal to I minus j plus k, it's essentially saying that v of 0 equals 1 minus 1 comma 1. And so we know that at this specific time t, when t equals 0, this is what the first component should be, this is what the second component should be, and this is what the third component should be. So when t equals 0, 2t squared plus c1 has to equal 1. Well, if t equals 0, then this whole piece is 0, so that tells me c1 equals 1. And we also know that 3t squared plus c2 has to equal negative 1. Again, t being 0, this is 0, so there's your c2. And the last one is that t plus c3 has to equal, c3 has to equal 1. And so if t is 0, then we get c3. And so we could say more specifically that our velocity vector is, let's make some space here, is 2t squared plus 1, 3t squared minus 1, and t plus 1. So we need that additional information about the velocity, whether it's the initial position or just, the initial velocity or just some random velocity. So if they told us what v of 7 was, and we got this vector, I don't know, 3, 10, negative 7, right, whatever. We just need something, right, some information about the velocity so that we can figure out what C1, 2, and 3 are. So in this case, we would say when t equals 7, this has to equal this, this has to equal this, this has to equal this. So let t equal 7 and solve for C1. Let t equal 7, solve for C2. Let t equal 7, solve for C3. Right? In this case, though, they told us the initial velocity, which is when t equals 0. All right, so now we have the velocity vector. So now if we do the integral of that, we should get our position vector. So the integral of 2t squared plus 1, 3t squared minus 1, t plus 1 dt would give us, what would that give us? It would give us 2t cubed over 3 plus t plus, let's say, c4. There's a constant that's going to be with that piece. Let's make this a vector, okay, comma. The next one would be t cubed minus t plus c5. And the last one would be t squared over 2 plus t plus c6. I use c4, c5, and c6 because I've already used c1, c2, c3 in this problem. I don't want to use them over again because I already said, these equal 1 and negative 1 and 1. So let's use different variables here. All right. And now what we want to do is we want to solve for that. That's where this initial position is going to come into play. So in this case, we know that r of 0 equals 1, 0, and 0. So when t equals 0, this here has to equal 1. So if t equals 0, I think we can really see that C4 is going to have to be 1. When t equals 0, this whole thing has to equal 0. That's this piece. So you see right away that C5 would have to be 0. And then when t equals 0, this piece would have to equal 0 as well. So you see C6 has to equal 0. So doing that, if you wanted to say, all right, well, let's make some space over here. The position vector, okay, let's put a little arrow on that one. The position vector should be 2t cubed over 3 plus t, plus 1. C4 was 1. And then t cubed minus t, and then t squared over 2 plus t. And that should be my position vector. Again, based off of this information that they gave us, we were able to specifically find C4, 5, and 6, 1, 2, and 3. But without that, we couldn't do any better than, say, this or this. Okay. But the whole idea here is if we know the derivative of position gets us velocity, we should know that the integral of velocity gets us back to position. And that's the whole point of this. One little bit of information I also threw in this slide here is that, an object traveling at a constant speed, we've talked about that, constant speed concept. The velocity and acceleration vectors actually end up being orthogonal to each other. That has nothing to do with this problem. I just have it thrown into this slide here in the notes for no apparent reason. But just since it's here, I'm going to talk about it. That's just something that you should know, is that when you're traveling at a constant speed, what happens is the acceleration and the velocity vectors end up being at a 90-degree angle with each other. So I'll show you a picture of that in motion in the next slide. So here, this represents one of those scenarios. So looking at this, the orange is the position function graphed out as a curve. Looking at the blue and the red arrows, you should take a quick guess as to which one is velocity and which one is acceleration. Thinking about everything we've said, hopefully you say that the blue is your velocity vector and the red is your acceleration vector. Why would I say that? Notice the blue is pointing in the direction in which you are traveling, okay? Seeing that point move, you see you're traveling up this helix. And notice that the blue arrow, the blue vector, is the same magnitude this entire time, which this tells me that I'm traveling at a constant speed, because the magnitude of the velocity is your speed. So you notice that. And then notice the acceleration in the red vector. The red vector is pointing inward the entire time. It's pointing in the direction in which I'm curving throughout this thing. So that's how I know that that's the acceleration vector. Also notice that the acceleration and velocity, the blue and red vectors, are sitting at a 90-degree angle with each other. Okay? So all this stuff is happening, but this is just giving you sort of a concept of, as I'm at a given position, I can't really pause this, I don't have that ability to do that while I'm recording, but as I'm sitting at a given position, okay, I see the velocity vector and acceleration vector, and this is just showing that happening all in motion.